Well, this afternoon we have the honor to speak with Larry, who's involved with the X-59 sonic boom test. So thank you, Larry, for being with us today on Do the Math.
Thanks for having me.
So what is your role with NASA?
I am a sub-project manager for the acoustic validation phase of the Quest mission. Under the Quest mission, we are building an X-59 X-plane that will be used to show that we can make aircraft that have quiet sonic booms on the ground.
Okay, so that's the goal, is to make those, which everything is going through the test right now, correct?
That's correct.
All right, so last year...
the Quest... Oh, go ahead.
Yeah, so in 2024, you guys tested the engines, but now you're ready for a flight this year, correct?
That's correct. Late last year and still ongoing, we are doing engine runs. We're doing our second engine run, about to do our third engine run here, hopefully either this week or next week. But you're entirely right. Just getting ready to fly. Our projection is that we will be flying the X-59 this year, 2025.
All right. Well, I understand that we need to worry about the sound, which is the big thing with the sonic boom. So what are we looking at now, Larry?
So this is the culprit. What we're looking at are shock waves coming off of an airplane or several airplanes that are going supersonic. These are military airplanes, T-38s and F-18s in some of those images. And those are your traditional supersonic airplanes that go faster than the speed of sound, break the sound barrier. And when they do, they create all those shocks. So all the lines that are coming off of the airplane on the right side are called shock waves. So anytime something breaks the speed of sound, shock waves are created. When you have a fighter jet, like what was shown in those images, I like to call those dirty airplanes when it comes to shock waves, because there's so many of those shock waves coming off of every time the airplane changes shape. So every time the airplane changes shape, such as the cockpit or the nose, all of those changes in shape cause a shock wave. And those shock waves travel down to the ground from where the airplane is flying, and that's what our ears perceive as a sonic boom.
Okay, and you were talking about how the cockpit might be different and the different heads on the plane as well. So I understand that there's at least two different ones that you guys use. And why do you use two? What have you found the difference in them?
The X-59 is very unique in that we have a very long nose. In the images that were shown, those fighter jets, the T-38s and the F-18s, have a relatively short nose and have very robust engines and wings because they're not worried about being quiet when it comes to a sonic boom. The X-59 is being designed specifically and strictly to make quieter sonic booms on the ground. So one of the biggest things that jumps out at people is the long nose. The nose itself takes up about a third of the airplane. So as opposed to a traditional airplane, the pilot is actually sitting in the middle of the airplane. In fact, when we introduced the pilot to one of the first models of the airplane, they joked, "Why am I sitting in the middle of this airplane instead of the front of the airplane?" And that's because those are some of the design features to keep the sonic boom quieter. That very long nose makes it so there's no sudden changes in the shape of the airplane, because again, all of those sudden changes are what cause shocks, and the shocks are what cause the sonic booms.
And that's that dirty shocks that you were talking about, right? Because of the different shapes, so that way you keep it. My understanding is that the pilots can't see over either because of the distance of that, which is why they have monitors in the cockpit with them. But
Absolutely.
Now I think we're going to talk about the sonic boom, also the run-through with the thumps right now.
So what we're showing here is a variety of different equipment that we use out in the field to measure the sonic thumps and the sonic booms of different airplanes, and we will do the same thing with the X-59. We call it the ground recording system, or the GRS, and it's essentially a suitcase that houses a bunch of very sophisticated electronics to allow us to measure the sonic boom on the ground, 50,000 feet below where the airplane is flying.
But flying at 50,000 feet, so it's significantly higher than what we would think of as passenger planes, usually flying at around 30 or a little bit higher than that, correct?
That is correct. Your typical passenger planes are going to fly between 30 and 33,000 feet traditionally, and there are several reasons why the X-59 flies a lot higher. One is the higher you go, the less the pressure resistance is, so it's easier for the engines to push you faster. And also at the same time, it's more distance that the sonic boom has to travel. And while it travels, the sound lessens and decreases. And so by the time it gets to our ears, it's a little bit lighter.
All right. Well, I think the third video that we've got is how to achieve a sonic boom with this test that you've got coming up.
Data off.
NASA PI, NASA PI, boom, stand by.
That was a banger on that, eh?
Report from the field. Primary array, secondary array, and tertiary array all got data. About 3 spiked microphones across the array. Max PSF was about 1.5 nominally.
NASA 1, NASA 856, first boom 8008, 38 seconds, second boom 7989, 44 seconds. Negative turbulence, ops check.
All right, so fascinating. But Larry, explain a little bit more about exactly what was going on right there, because I thought I heard one of those booms right there.
You definitely heard those distinct double booms that you get from an airplane that's going supersonic, and absolutely we're trying to lessen or quiet that sound. So a lot's going on there. When we have a test flight, traditionally we're on the radio with the pilots. We let them know when we have heard the sonic boom or the sonic thump on the ground. We also communicate with the rest of the team what kind of sonic thump it was. For that particular test, we were looking into the effects of the atmospheric turbulence on the sonic boom. So in that video, you heard me mention spiking. The atmosphere close to the Earth can make sonic booms sharper, or spike, if you will, or it can make them a little duller or rounder. And so those are the types of feedback and information that we relay during a test.
Okay, and this is a free fall going on also, correct?
We perform a maneuver that's called a low boom dive maneuver.
Okay.
Right now, we don't have the X-59 airplane. We're still building it. But for decades, we've been doing a lot of flight research on quiet sonic booms. In order to make those sonic booms, we do a specialized maneuver called a low boom dive that takes an F-18 fighter jet. The fighter jet flies very high in the sky at about 48,000 feet. It then does a dive, as being shown here. It does an inverted dive. It reaches supersonic speeds as it does that dive, just for a brief second of time. And that's when your sonic boom is generated. And so we have been using that maneuver with F-18s as a surrogate to X-59's quiet sonic booms.
Okay, so that maneuver, that dive, is kind of what I was talking about with the free fall, as far as a layman looking at it, something like that. Because with other aircraft, a plane will go up and practice with a stall or something like that. So it's just kind of but you guys are going a lot faster, doing a lot more things right there. So as far as decibels go, we've only got a couple of seconds here. Is there a certain range that you're looking for to say, yes, this is now going to be acceptable over land as opposed to just over water?
Yes, absolutely. So we deal in a different flavors of decibels, if you will. And one metric that we use a lot is called PLDB, or perceived loudness in decibels. And that is just a different way to characterize a decibel based on how the human ear perceives a sound. So for the X-59, we've done a lot of research over the years, and we've determined, and NASA has determined, that 75 PLDB is that target that we believe will be acceptable amongst communities.
All right. Well, Larry, thank you. Acoustic validation, keep that going on. We'll keep our eyes and ears to the sky and hopefully not hear as much. So, Larry, thank you once again for joining us today on Do the Math, and we'll be back with more right after this.